Right. Hello, everyone. Today for cats, we've got Diptarka Chakraborty from National University of Singapore here to talk about tight lower bound on equivalence testing in the conditional sampling model.
Thanks for the introduction. Yeah, so today what I will be talking about is about some sample complexity for this sum distribution testing problem. And this is a joint work with Chakraborty and Gunjan Kumar, who is a postdoc with me. So before starting the talk, so I will try to be as less technical as possible. I will not go into all the proof details because then it becomes very complicated. So I will first try to give an overview of this, which problem we want to solve and how we can approach those problems, and then try to give at least very high level overview how we get our result, and then finally end up with some of the interesting open questions. So what is distribution testing? So this falls under this regime of property testing problem. This is the larger class of problems. So here in the property testing, what we are interested in, we are given an object. And then we want to test certain properties of it. And once this object is a distribution, some probability distribution, then it is basically the distribution testing problem. So here, so one thing to note is that when I say that we are given a probability distribution, so then what I actually mean that we have some kind of query access to this distribution. It is not like we can really look into the distribution itself completely. Because if we could, then basically everything becomes trivial. So we have some kind of query access. And with those query access, what we want to test, I mean, is certain properties of those input distribution. For example, I mean, it is not really property. I mean, you can think of like some estimation problem. Suppose I want to estimate the support sets. So like how many non-zero probability elements are there in this distribution. So if we want to think of like property, you can think of like whether it's large or small size. Then another thing we can try to test, say, whether it is close to uniform or not. And there are many such natural properties that we want to test. And there are also many quantities we want to estimate. So for example, the support size, or we want to maybe estimate, say, entropy. But our objective should be we want to make as few query as possible. Okay, so generally these domain sizes are huge. So now let's start with a very simple example. Okay, so suppose you have a point and you want to test whether this point is fair or not. Right here, I mean that probability of head and probability of tail is exactly how. So now, given this coin, so suppose I allow you that, okay, you can maybe flip the coin a few times. Now, how many coin tosses are required to basically decide whether it is fair or not? And then a more general version is like, suppose you are given some lottery machine which picks some random numbers from 1 to n, and you want to test that whether each number is equally likely or not. Then how many samples are basically? Because you can guess that if your lottery machine, if you are buying lottery and your lottery machine is biased, and then highly likely someone else can use that biasness and get lots of money and cheat you. And then you can actually maybe this nice story about this lottery scandal in Pennsylvania. So where you will see that how somebody actually misuses this biasness of the machine and gets lots of money out of it. So now, if I ask you to do test all these tasks, if you think for some moment, you will realize that it is almost impossible. I mean, we cannot do. I mean, if I tell you like given a point, I want to ask you like exactly whether it is the probability of head and tails are half or not. If it is this type of exact question, then you cannot actually solve it with a few samples. So that's why we will slightly relax this problem and try to say that, okay, now we want to test. So we want to basically distinguish between two cases. Whether the input satisfies certain property, then I should accept, or it should be, the input should be far from anything that will satisfy that property. So I will come to the point, I mean, how we define farness. But these are the two things we want to distinguish. And one thing also I should note here that with lots of samples, then actually all this problem becomes in some way trivial. Basically, with lots of sample, we can, I mean, there are results, we can basically learn the whole distribution up to some small level. And if we can learn the whole distribution, then testing all these properties are easy. So that's why we should be looking for like very few samples. Okay, so now if you now go back to this simple example, so now what will be our modified objective? So now we want to distinguish these two cases. The first one is when your probability of head or tail is half, so basically the coin is fair, then we want to accept. Or we want to reject when, so it is far from being a fair. So basically probability of head is way greater than half plus epsilon or less than half minus epsilon. So at least there will be a significant bias in one of this side, either head or tail. Then we want to reject that thing. And okay, so now the question is how many coin tosses are required? Can any of you guess? I mean, just by using like simple application of Charnow bound, you can show that something like 1 over epsilon square samples sufficient. Okay, so now, as I mentioned earlier, so once we have, we allow lots of samples, so basically linearly many samples, then actually one can learn this distribution, any distribution approximately. So then it becomes trivial. And these problems, I mean, all these properties, I mean, they are basically very fundamental in nature, and appear everywhere in the statistics, data analysis, and these days machine learning communities in lots of places. So now, one thing that I have not so far explicitly mentioned, that what do I mean by this query or sample access? So there are different models. So one of the most easiest or the natural model is like when your distribution D, what you can do, you can just get some independent sample from it according to the corresponding probability. So basically, you can sample a point A with probability D of A. So where D is this input distribution. And this is the most natural sampling model, and all these problems were initially studied under this model. But it turns out that although we can get many non-trivial results, but it turns out that this model is not that powerful. For many problems, many natural problems, it turns out that we need lots of samples. So there are certain properties for which we need at least say n to the 1 minus c sample. Even like, for example, one of the basic thing that we want to estimate generally for probability distribution is what is the support size. And it turns out that in this model, we need almost linearly many queries. So n over log n many queries are necessary. So that's why people now started looking into, okay, what are the more powerful model that we can start. And that should be also like practically relevant. So, and that's why there are many suggestions and people have looked into many models. So for example, one of the thing is called probability revealing. What is probability revealing? So previously we were saying that I can get a, okay, so here only, so I am getting each point A with probability dA. So this is just I get a sample. Now, suppose together with this sample, I also get to know this value of dA. So once I get this A sample, so together with I have this value of dA. So this is the probability revealing model. So this is definitely more powerful than the sampling model. So then the question was how we can leverage this information of probability and how efficiently we can test certain properties. And then people also looked into like, okay, maybe getting this exact value of dA is not that natural. Maybe we will not be able to implement it, but sometimes we can at least approximate or estimate this value of dA. So suppose I give you this estimate free of cost up to some additive error. Then whether we can use it, that is called approximative probability. And then there are many different other models, I mean, just by combining it with sampling. And then, so this is like getting some value of the probability. But in other ways, so there was another line of research where people consider this conditioning model. So this is still a sampling model, but now we allow the sampling to be according to a conditional probability distribution. So, and this is the model that I will be talking about. So let me now define this model. So here, what we have, so again, V is this input distribution where we can have this some query access. Now, what type of query access we are allowed? So now, any algorithm, what it can do, it can specify some subset of the whole domain. And that what can feed into this query. And now what it will return, this oracle will return me is some element A from this particular set. Okay, with the corresponding conditional probability. So the probability of returning this A will be dA by d of this pulse. But one thing we have to be a bit careful that we have to handle the situation, because since algorithm has no information like what is the probability mass on this particular set, it may select something or give as a query some set which has basically zero probability mass. We have to handle those cases carefully. So when this model was introduced initially, so by two independent work, so in one work, so the authors do the following thing. So they use this convention that if the probability mass over A is zero, so then I will return just some arbitrary element from this A uniformly. But in another work, I mean so this set of people, so they basically say that okay, maybe once this happens, I can actually detect that. Maybe I can return that okay, so this dA is actually zero. So in one model, we don't have that information that whether dA is zero or not when I query with a subset, but in other model, we can get also that information. So this is modulo this thing, these two models are essentially same, introduced by these two group of people. And it is not clear like which one is actually more powerful. I mean, apparently you can think of like, okay, maybe if I can, when I specify a subset, if something returns that if it is mass is zero, if it is returning that information, then it is more powerful. Yes, but so far we don't know how to use that information actually. Actually, I am not aware of any testing algorithm where actually people really use that power. So that's why most of the algorithms that we are aware of at this moment, that basically works in both the models. Okay. So now, so what are these subsets? So I mentioned that this algorithm can specify this subset for condition. Now, if you think of from the upper bound side, that we want to design an efficient algorithm, then definitely this subset should not be like an arbitrary subset. Either it should have some small size, there should be some small size subset, some bounded size, or it should have some kind of small description. So generally, so far, either so whatever the known testers are for some of the interesting problems. So either this conditioning are like very specific type of conditioning, like something called clear condition. So where basically these subsets are of size 2. Or this is like some interval condition. So like you just, so you can think of 1 to n and you just give 2 indices. And now this will give you an interval and your set subset is that particular. Or it is some subgroup. So this is like one type of conditioning, or this has some kind of implicit description, like somebody gives you like, okay, so I want to condition on some subset, which is generated by picking every element from this domain with certain probability. This is like some short description you are giving. But yeah, apart from that, I mean, although I mentioned here that subset with short description, so far there is no formal notion of such short description that has been used in this. But this is on the upper bound side. But if you want to think of from the lower bound side, so like suppose you want to argue that, okay, so if you want to solve some problem in this model, you need at least this many queries. Then we allow basically arbitrary subset. And we don't know how to leverage on like really short descriptions subset. So if we have like something like bounded subset, bounded size subset, for example, this pair conditioning where we have only 2, I mean subsets of size 2, we only allow. So then actually we know using communication complexity, we somehow shows for certain problems some strong lower bound. But for arbitrary size subset, we don't know much for general problems. Okay. So is this model clear? Okay. So now let me give some comparison between these two basic models. I mean, the SAMP, and one hand we have this powerful conditioning model. So it turns out that this conditioning is actually really very powerful. So we can do many things that we cannot do very efficiently in this basic sampling. For example, if we consider this uniformity testing problem that we define earlier.
Is that the probably removed one?
No, there is no probability revealing. So I'm just considering picking some. So the most named one. So now if you consider the uniformity testing problem, so then for SAMP model, we need actually square root in many samples. I mean, that is basically necessary and sufficient. On the other hand, in conditioning model, we can actually solve it in or using only order 1 queries. So here I am hiding that epsilon part when I say that something is epsilon part, although I have not defined so far this hardness. I will define later. So there is some dependency on 1 over epsilon, but on the domain size, there is no dependency. So now for the support size estimation, so then as I mentioned earlier that for SAMP model, you need n over log n. But for conditioning, suddenly if you allow this conditioning sample, this sample complexity drops down to just log n. And for equivalence testing, we will see later. So another important thing between these two models is that if you think carefully, this SAMP is inherently non-adaptive. Because since you are getting all this sampling and samples from the distribution, you can just get all these samples beforehand and then run it. It is essentially non-adaptive. But for conditioning, it is not the case. It could be adaptive as well. So once you select some subset, depending on what sample you get, depending on that, you can generate the next subset to query. And that actually gives conditioning more power. And also from the lower bound side, it makes our life much more challenging to show some non-trivial one. So as far as I know, so when this model was introduced, it was solely from theoretical perspective. People were interested only to study theoretical. But surprisingly later, it turns out that this model actually, I mean, this conditioning model, one can actually implement very easily using some sets of sampler. And that's how it finds application in all these formal methods, machine learning, probabilistic programming. And also recently, we also find some connection with approximate model counting problem. And then we can show non-trivial result from techniques. This conditioning sampling distribution testing. Okay, so now let me come to the main point that what is the equivalence testing problem? So in the title, you have seen that I am going to talk about equivalence testing, but so far I have not defined it. So what is the equivalence testing problem? So in this problem, you are given two distributions. Okay, so basically you have sample access to, some query access to both the distributions. And your objective is to decide whether these two distributions are exactly same or one is epsilon far from. This is, you can think of like general version of this uniformity testing. In the uniformity testing, one of these distribution also. And now let me define what I mean by epsilon far. So essentially, we consider the total variation. It is just essentially the L1 distances multiplied with half. So what is known? So if you consider this simple sample model, so then this is basically well settled. We know that it requires n 2/3 by epsilon to the 4/3 or square root n epsilon square, whatever length of in theta of it is the query complex. But for conditioning model, so for the upper bound, again, the dependency on the domain size is log log, so it is log log n by epsilon to the 5. But on the lower bound side, we only know that it is square root log log. So there is this quadratic gap between the upper and lower bound, and that has been basically a recurring open problem. And it was also listed as one of the open problem in this sublinear.info. And so now I should make some point here. So if you look into this lower bound, so this is not just lower bound for the equivalence testing problem. So in the conditioning model, for many other problems, that was the lower bound. Even for, say, support size estimation, that was the known lower bound. And somehow it turns out that whatever the previous known technique, so there this square root, we cannot get basically better than square root log log n just by using that previous technique. So there was some kind of barrier. And so later, before this work, last year in some another work, we did this barrier for the support size estimation with some different technique. And we basically close the, again, gap between upper and lower bound. But there were a caveat in our technique in the sense that we need the distribution, the hard distribution to be of certain type, which is not that naturally occurring. So, and also that technique, we don't know how to lift it to the equivalence testing problem.
Right. And it's a 20, right?
N is the domain size.
Yeah.
It's not support size, it is domain size. And you can see that the support size problem and equivalence testing problems are completely different in the sense that it may happen that two distributions are very close by, but their supports are very different and the other way around. So that's why it is not the case that if we get lower bound for one, then we'll get lower bound for that. But what we show here is basically we design a new technique. So it is not completely new, I would say. So we basically use some extra new tools and append it with the previous framework and beat this square root log log n barrier. And what we show that for equivalence testing, we can get essentially omega log log n lower bound. And this is not just, this result doesn't just hold for the equivalence testing, it also holds for many other property testing problem. And even for the support size estimation also, we show that using this technique, we can get the similar result. Okay. So that's about our result. And now let me give you a very high level overview how this argument should work. So before that, I have to recall what was the previous argument, how we actually previously we can get square root log log n. So for that, we need some notion. So first, one important notion that we want to define is the atom. Suppose you have a series of a sequence of subset. Say suppose some subsets are there. Say this is A1, A2, A3. What are the atoms? So atoms are basically all these 2 to the I distinct subset defined by, so this is one atom, this is another atom, this portion is another atom. So basically all this possible 2 to the I distinct subset, they are, we call them different atoms. And the remaining are basically, so if this is the domain, so basically this is also another. All these 2 to the I subsets, we call it atom. So now previously, so when people argue about conditioning, lower bound in conditioning model, as I mentioned, that conditioning model is very powerful because first of all, it can be adaptive. Second is that this subset size could be arbitrary, and that gives us lots of choices. And somehow we cannot directly use the decision tree method. I mean, generally how we prove lower bound in query complexity lower bound. We generally look into the corresponding decision tree model, somehow try to count the number of leaps and get some lower bound on the table. But if you allow this arbitrary size subset to condition on, then the possible options are huge and we cannot get any non-trivial bound. And what previously people show is that for certain type of properties, actually there are some structure in the algorithm or the tester in some way that it is not really like we need to use this fact that these are all arbitrary size subset, and we can prune basically lots of possible options by saying that the tester, although we can do arbitrary size subset conditioning, but tester will not really use that fact. It will use certain properties of those samples. And now we have to formally define what are that certain information of the samples that actually tester uses. And that will basically prune the decision tree. And then we can hope to get some non-trivial order. So one of the important notion is that configuration of SI. So what is configuration of SI? It is very simple. So suppose you have you can think of like one run of testing algorithm. So at each step, you this algorithm will specify some subset and get some sample from that subset. Now suppose these are basically this subset. So this is the first subset A1, and you get some samples small s. This is A2, and you get something from here. S2 and so on. So now, for a particular sample Si, what is its configuration, or what I will say that what information actually really the algorithm will use is the information is the all this label invariant information. Because if you think of this equivalence testing problem, this is a label invariant property in some way. It doesn't matter what are the labels of the corresponding elements. Even if you apply some permutation on the label, if two distributions are equivalent, they will still remain equivalent. And if they are far, still they remain far. So now for a particular SI, what are this label invariant information that are really useful? One is in which of the unique atom this SI belongs to. So if you think of in the previous thing, so now if you have three subset that you say queried on. So now it defined all these 8 distinct atoms with distinct states. And now SI I want to import this SI in which atom it belongs to. So suppose I say that okay, this belongs to, so SI belongs to here. So that means that it belongs to both A1 and A2, but it doesn't belong to. So this is one information we actually have to use. And second information is that whether this SI has a collision. What do I mean by collision? That whether this at particular step, whatever sample I get, whether that sample I already have seen in the earlier steps or not. And if so, then which of the previous samples actually is same as this particular sample. So this is what we call configuration of a case. So now you can see that to encode this configuration, we need at any step I, we need only two I minus 1 bits. Because why? Because previously we have I minus 1 samples and also their corresponding sets. Now, if I can encode that this particular sample Si belongs to which of the previous AIs, so then it automatically gives us that exactly which atom it belongs. And also, if I can specify that in with which of these samples it collide, then we know that what are these collisions. So that gives us this 2 to the 2I minus 1 bits of summation. And now later I will show you that this actually prunes the decision tree. So now we will formally define this special type of testing algorithm, which later we will argue that the general testing algorithm and the special types of testing algorithms are essentially works very similarly for certain types of problems. And since this is a special type of testing algorithm, we can show that it has small number of nodes in the decision tree and then argue lower bound in this case. So this special type of testing algorithm is called code adaptive tester. So what is code adaptive tester? So here we will, so if you recall in the conditioning case, the algorithm will specify some subset. So now here we will argue that, okay, so these subsets are not arbitrarily chosen. It has certain type of structure that the algorithm will specify, and then we will choose some subset uniformly at random that satisfy those structure of the property. So what are the things that algorithm will actually specify? So algorithm will basically specify. So if you recall previously, I defined all these atoms. So now for all these specific atoms, so algorithm will specify some integer ki. So for this is suppose the ith atom. So for each atom, it defines some integer. What it represents that whatever be my next query set, what will be the intersection size with this particular atom? So how many elements from this atoms basically will be part of this next query set? So this is what algorithm will specify. And second, the algorithm will also specify which are the previously seen sample that should be part of the query. These are the two things that algorithm will specify. And once the algorithm specify that, then actually algorithm will just select some subset uniformly at random that satisfy these two information. That it should have intersection size with all these atoms with this integer ki, and those are the seen elements it should. And then that will be my next queries. You can see that now the query sets are very structured. These are not like arbitrary query sets. And previously this CFGM paper, they show that for any labeled invariant property and also for equivalence testing, if there is a Q query general testing algorithm, then we can also have a Q query code adaptive tester, this special.
Could you mention the property again?
Sorry?
The two properties you mentioned.
Here.
Yeah.
Yeah, so here, what are the things? So here basically, algorithm will, instead of directly defining what is the subset to query on, it will essentially gives us some integer, a set of integer, which denotes that whatever already, so whatever the query set, we have already made the query on those subset. If you consider all those 2 to the I distinct atoms, so now from each of the atom, how many elements I should consider in the next queries. Just this how many, not the which are the elements. Just how many elements it should be, it should consider. And second is that which are the previously seen samples? There are S1, S2 up to Si minus 1. Which are those? Maybe S2, maybe S4. This I will include. So only this is given by the algorithm. And once it is given, then algorithm will use its internal randomness to just sample some query set that satisfy these two. So now basically we can now, without loss of generality, from now we can assume that our case study is this special type of case study which is code adaptiveness. And now how this code adaptiveness actually helps us in getting square root, log, and power. So now, for any testing algorithm, if it is deterministic, then we can consider the corresponding decision tree. And as I mentioned that if we consider general tester, then this decision tree will have lots of nodes because this subset would be arbitrary size and each will give you basically this arity of each of them. But now, since suppose the height of the decision tree is Q, because this is a Q query decision tree. So now if you look into this description, you will see that what it matters is essentially this configuration of this. For each of the node, what will be the next query? That only depends on the current configuration. Given all the previous nodes are, we know the path up to this height. And now since the configuration we can encode using twice I minus 1, which is basically at most twice Q bits because these are Q query algorithm. So then, how many possibilities are there at each? It is essentially 2 to the 2Q. So that already gives us a bound on the arity of each of them. So degree of each node now becomes at most 2 to the order. And as a result, what we get that this decision tree will have at most 2 to the order Q square many nodes. Since this is a depth Q tree. Okay, so this already gives us some kind of sparse decision tree. It essentially prunes many possibilities. And once we have that, and then what they show is that in this previous paper, they give some hard distribution and show that given this hard instance, one needs at least square root log n nodes in the decision tree. So then if you now combine, so since the decision tree has this 2 to the Q squared, so this basically has to be square root log n, and that will imply that your Q has to be omega log, square root omega log. And that is where this square root comes. And this notice that the square root comes because here we have 2 to the Q squared. So now what we do? So again, our framework is like we first define this hard instance, yes and no. And now we replace this conditioning query with some kind of weaker version of the query. We call it weak conditioning query. So even restrict ourselves to a weaker query model. And then what it helps us in further sparsifying this decision. So previously the number of nodes could be 2 to the Q squared. Now we using this weaker conditioning model, what we show that this decision tree would have at most Q to the order Q nodes. So this is basically 2 to the Q log Q. So from 2 to the Q square, now we have 2 to the Q log Q. And once we have that, then we use similar type of idea. It is not similar, technically it will be different, but the high level, it should basically, again, we will argue that 2 to the Q log Q should be at most at least some square root log n or some poly log n. And then we get Q has to be omega log. So now one case is that after all this argument, what we could show that with respect to that weaker conditioning model, we can get omega log n lower bound, which is our intended lower bound. And then next step was that we show that for the equivalence testing problem, the whatever hard instance we construct, for them, actually this conditioning and weak conditioning model, if we consider both this testing algorithm using conditioning and weak conditioning, their outcomes will be basically indistinguishable, as long as your number of queries omega log. And as a result, so you can think that if they are indistinguishable, then if suppose in the con model we can get a better query algorithm, then in the this weaker con also we can get a better con, but which already contradicts that in weak con we need omega log. So that's how we lift this lower bound from this weaker conditioning model to the. Time to any that?
About 20 minutes.
20 minutes? Okay. Then I can give you more ideas. Okay, so is this high level picture clear? Okay, so then let me go slightly more into it. Okay, so let me actually skip this part. So just a quick recap. So if you recall, this special type of testing algorithm that we consider was a poor adaptive tester, where the conditioning set are of a very specific type that the algorithm will only specify that for each of these atoms, how many elements to include in the next query set and which are the previous sample. And after that, we just pick this set randomly that satisfies. So now, let's look into this conditioning query. So now if you look here, so this cond on this AI. So how actually it will look like? So we defined previously cond as just it will give us some sampling, some sampling with the condition. So now alternatively, we can also visualize in the following way. Because now our AI is of this form. Some UI and OI. What are UI? So these are basically, so these are scene elements. Because if you recall, so these were basically whatever the some subset of previous samples. And these were fresh element or unseen element, which we get by specifying that how many unseen elements from each of these atoms are shooting. These are the two types of. So now, can visualize conditioning query in the following way. That first, it will pick either this one of the elements from this already sampled element or this unseen set itself. So just try to visualize in that way. So I mean the algorithm will not perform in that way, but you can try to visualize in that way, that either it will sample something from OI or it will sample this whole subset as it is. And each OI, element from the OI, it will just pick with this corresponding condition probability. And this UI also pick with the corresponding. And now, if this one element from OI is selected, then that will be basically my sample in the next. But if this particular set of unseen elements is seen, so then we further pick a atom with a conditioning probability, and then finally we pick something from that particular atom. So that is how we can visualize the general con. Now in the weak con, we just tweak a bit this way. What we do? So here, so everything will remain same. So the only place where we make the change is that here, each atom in the normal query, it should be selected with the conditioning priority, corresponding conditioning priority, which is dv by duy. So now, so this is dependent on the input distribution. Now in the weak cont model, we make it independent of the distribution. We just say that these are just selected with priority size of p by size of p. It has nothing to do with the input distribution. And why that helps us in some way? Because now you can see previously it was dependent on the input distribution. Now it only depends on, still I pick it randomly, but with this priority. So that is, it only uses the internal randomness of the algorithm. So now, if you consider the corresponding deterministic part, then basically these choices will be completely gone. Because this is the place where actually I get that 2 to the q dependency, because this is where I basically get all the possibility of which atom this sample actually belongs to. So now if that part is gone in your deterministic part, then what are the only options? The only options are which are the previous samples it belongs to, or it is a fresh sample or not. So this only gives us q plus 1 possibility instead of 2 to the q. So that is where this weak con model helps us in sparsifying the decision tree. So now at each node, instead of 2 to the q, we have only q plus 1. And as a result, the whole number of nodes in the decision tree will become q to the q order.
If you have to keep up. Okay.
So once I replace this with this term, so now it is independent of the input. So now it completely depends on the internal.
It still depends on UI though, right?
It depends on UI, fine, but UI also depends on how we define UI. Let's recall. So UI is also selected using this randomness of the algorithm, right? Because algorithm specify how many fresh element I should consider from each of the atom, and then it uses own internal randomness to select. So this UI is also selected randomly using completely the internal randomness. Now, when we consider the corresponding deterministic counterpart, when we draw this decision tree, then that internal randomness will be gone. So this will be fixed. So now UI will be fixed, this D will be fixed. Now when I sample, there are only q plus 1 possibilities. Which of the previous sample it belongs, or whether it is a completely fresh one or not. And that's why from 2 to the q we get q. Okay, so now small thing that I want to highlight, I mean, I will actually not go into the details, but just I want to give you some glimpse of like what could be the hard instance. Where actually, so you can ignore this whatever I have written here, so you can just focus on what I'm going to draw. So the hard instance will be of this following form. So the distributions, you can think of this is over a random subset, where the subset size is random and also the subset itself is random. And then we basically distribute the probability mass in this almost sub-polynomially decreasing way. So basically, we divide the whole thing into small bucket, where the bucket size are increasing sub-polynomially. And in each of the bucket, so in all these buckets, the total probability mass is same. So these all are equal probability mass. So that's why in each element in the buckets, their probability is decreasing sub-polynomial. And now, so this is like the main framework of the hard instance. Now, if you recall that in the equivalent testing, we have to consider define two distributions. So now So this is basically one distribution, what I described. So now suppose in the yes instance, you are given basically both as same distribution. So this is the yes instance when they are. And on the no instance, what you will do, you will give this distribution and you create another distribution from it. And how you do it? You basically look into each of this bucket and again randomly partition into two. Okay. And then suppose this is your randomly partition into two equal halves. And in one half, you decrease the probability, and in another half, you increase the probability. Same amount. So basically, if you look into one particular, if you focus on the one particular bucket in the yes instance, I mean the one distribution, so all the elements has the uniform probability in that particular bucket. In another one, in half, it is basically half less than this, and another it is half more than this. And this is how we get yes and no instance. Because now you can see that if your input is of this form, that one is this one and another is this particular one, then you can show that the total variation distance is actually 1. So that gives us a no instance. Okay. So now, what we want to show? We want to show that any co-adaptive tester with this conditioning priority, when you are given this hard instance yes and no, it should require omega log inquiries to distinguish. So how it works? So this is what we want to show, that yes and no instances are distinguishable by a decision tree unless the height is at least omega log. So for that, yeah, so now it will become more technical, so I will skip mostly. So, but on the high level, what I will try to say is that, so now we will look into the decision tree, and for each node, we define some event. So we basically define some nodes as good node and bad node. Okay. So roughly speaking, what we say a node is good if. So if you recall that in each node, basically we specify some subset to condition. Now we will see that this particular subset, what is the intersection size with each of this bucket? So depending on this intersection size, second, on how many bucket it actually has a non-empty intersection with, and what is the priority mass. Depending on these three quantities, we define whether some node is good or bad. Okay. And then we finally argue that what is a good event, that if your testing algorithm doesn't pass through any band. So and then finally, what we argue that okay, so when no matter whether the instance are yes or no, the probability that this your algorithm will pass through some bad node is very small. So the good event probability is basically 1 minus small o of 1. And here we use the decision tree table. And now once this good event happens, then we argue that the outcomes of this, now you have, in one hand, you have a co-adaptive tester where you have this conditioning query. And in another hand, you have co-adaptive tester with weak conditioning query. So then we argue that given this algorithm doesn't pass through any of these bad nodes, they basically in the lead, they are indistinguishable. So how we argue, we basically consider the total variation distance of the distribution of these nodes in each of the level, and then inductively we show that even at the leaf level, they are very close. So they are distinguished. And as a consequence, we finally lift the lower bound for weak conditioning. So that is how it works. Yeah, I know that this is like a very high level because there are lots of things that actually I deliberately hide. So now few things I want to specify before the talk. So one thing that I mentioned that it also implies a similar lower bound. So now I should give you some that if you recall that in the hard instance, I say that I will first choose the support size randomly, and then also choose what are those elements also random. Now, if one may wonder, like, why I choose this support size random? Actually, one can observe that if I know the support size beforehand, then if we keep the remaining hard instance construction same as it is, then actually with only a few queries, we can actually distinguish this yes and no. So yeah. So that's why, so basically it says that if I know the support size in advance, then only extra number of conditioning query we need to distinguish this yes and no case is just constant. And at the high level, why that happens is because if you recall, so suppose you know the support size. So then you try to construct a conditioning set on which you will make this query. So you pick each element with priority C over S. Then roughly from your support, you pick some constantly many elements, since S is your support and C is some cleverly chosen constant. And now in our instance, if you recall, this buckets are of growing size. So now if you look into this bucket where each of the element, I mean the bucket where it has the largest size. So at least constant fraction of this constantly many sample, they are from this particular bucket. And also even in this each bucket, even if you divide into two equal size half, each half is actually significantly greater size of the previous buckets. So then basically at least one element from each of the sub bucket you will pick. And once you pick that, then actually distinguishing is easy, because in each of this, I mean now the gap of probability is this 3/4, because in one hash you have 3/4 and another you have half. So you have this constant gap in the probability. So now you can use pair conditioning to distinguish whether you have this distribution of that size that type, or it is uniform over that particular. So that's why with extra constantly many queries you can identify or distinguish. So that's why the similar lower bound for this equivalence testing also directly gives us the same lower bound. Okay, so now a few open problems to state. So one thing, as I mentioned, that this conditioning model itself is very adaptive in nature. I mean, if you want to use the power of conditioning, then it should be adaptive. So now people also have looked into the non-adaptive version of it, because the non-adaptives are essentially gives us more parallel algorithms. So then the question becomes, say, for equivalent testing, so how many samples are necessary and sufficient if we consider non-adaptive version? So then there is a huge gap. So currently for the adaptive version, if we only want to consider the dependency on the domain size, the gap is closed. I mean, it is log n and this is omega log n. So up to some small poly log factor, it is that. So, but that is not the case for a non-adaptive version. So here upper bound is log to the 12, whereas the lower bound is only log n. So now one question is, can we close this gap? So very recently, actually, what we showed is that we can close the gap if we allow just one round of error. You first specify some query set, see the sample, and then specify another set. This is just like one round of error activity. Then you can solve it using order log. But in general, if we don't allow this extra one round, then it is still open. So yeah, so here are the now open problems. So one open problem is like for the general adaptive tester for the equivalent testing. So whatever result we have, this only close the gap on the dependency on the domain size. But there is also a dependency of the F sub. So currently there is a gap. So as far as I know, for the upper bound, the dependency is 1 over epsilon to the 5, whereas lower bound it is 1 over epsilon. So what is the exact difference? And and then what about this non-adaptive test? As I mentioned, can we get a tight bound for the non-adaptive test or include the lower bound? And
You mean like depends on epsilon, right?
depend on epsilon and also on the domain size. Because for the non-adaptive version here, as I mentioned, the upper bound is log n to the 12 and here it is log. So here on epsilon square also is a gap. But even for the domain size, there is a huge gap.
So the bound you were stating, you were stating the depends on epsilon, though, like something against positive epsilon.
Sorry.
The bound you were stating, because there wasn't an epsilon.
Yeah. So the bound we are saying we just consider it to be some fixed constant epsilon. So yeah, it is not dependent on epsilon. So that's why for the adaptive version, so the gap is still. And for the non-adaptive version, the gap for this size, I mean domain size as well as epsilon both are. So what we can show, I mean that with one round of adaptivity, we can close the gap. But the question remains for pure non-adaptive tester, what is the true dependency on domain size? And also another, I think this also is interesting, like whether there is a trade-off between this adaptivity and query complexity. Like as I mentioned that just one round of adaptivity, you get some log n over epsilon to the 9. Now maybe if you allow 2 rounds of adaptivity, can you improve the dependency on epsilon?
Are there any problems where there is no like a separation between the, like a form like the lower bound that justifies?
So you mean on this adaptivity?
Yeah.
So there are actually a hierarchy theorem for adaptivity. So basically one can show that if you allow just one round of adaptivity with this sample complexity, you cannot solve certain problem. Yeah, so basically, okay, so if you fix some k round of adaptivity, then there are some problems which you cannot solve efficiently in k minus 1 round. Okay, but these are like all existential errors. There are some
There's no
problems.
like famous problem, like no.
At least I am not aware of. Yeah, so these are like some of the interesting problems and yeah.